I thought it'd be a pretty good idea at this point to start explaining how this sort of virtual system works and how the virtual camera, if you like, works. Here we have a top-down view, if you like, of an environment, a 3D environment. And we have our camera set up at this point here, so it's at 150x by 300y. And then I'm going to have a wall that's between 100 and 150x there, and 150x, 200x there, and that makes up two segments of a wall. Now, as you can see, I can produce lines that are the hypotenuses, if you like, between the point that makes up my focal point, my virtual camera's focal point, and the points that actually make up the wall as well. And from this I can actually work out some angles using some very simple mathematics. In this particular case I'm going to be using a mixture of Pythagoras' theorem and some other geometry such as trigonometry. So if we start with looking at the values and the way that the camera has to work, I can work out how far away each of these dots are on my virtual camera, and then I can draw them to a virtual camera screen. We'll be going back to this picture in a short while. If you imagine this is our virtual camera, we have a focal point of our camera, the dot that appears on the actual level file or whatever it is that we're actually talking about, and then we have a length between the dot and a virtual screen, and we call this the focal length. We also have a viewing angle, and our viewing angle is the distance that makes up our virtual screen as we go further and further out. So without needing to have to worry about an actual resolution to our virtual screen, we can actually know straight away what we can see and what we can't see based on this angle, because any item that we have in front of our camera obviously produces an angle as well between the different points. So if I was to have an angle from here to here, as long as the angle between the straight ahead focal length and this line is lower than the angle of this viewing angle, that item is in the view of the camera. This is going to be important for the next thing that can actually cause a major issue when we are looking at drawing our items to our virtual screen. Now, the big problem lies with the lens, if you like, itself that makes up the virtual camera. Say we have got the situation that I showed on that drawing, where we've got two walls in front of the camera. If I measure this length between the focal point and the wall here, the distance is going to be 200 exactly, because it's all on the same plane. But the lengths for these two points are going to be slightly greater because they're the hypotenuse of a triangle. In actual fact, it's going to be 206 pixels in length for each of these two angles, because the angle's 14 degrees. I only know this because I've been working obviously this on a computer and on a spreadsheet as well. So the problem becomes, instead of actually seeing a nice straight line, as you might expect, of walls because they're directly in front of you, you might expect to see something along the lines of this. Apart from that, line looks obviously not very straight. What you actually get is more like, although this is slightly over-exaggerated, like this, because the points at the end, according to the calculations, are much further away, a whole 6 pixels away, in comparison to the ones in the middle. Now this is what I mean by a lens effect. The closer the item is to the edge of the camera, the more this lens effect is apparent. Now the way that we actually translate the wall to actually appear on our virtual screen is we're using congruent triangles. We're using the angles that they make with the focal point, then working out the angles that they make with the screen, and then drawing it in the right location. We can actually take this value and we can do some extra calculations to try and counteract the lens effect itself. So if we have our screen here, and we've got our actual wall here, we know that the calculation produces a value of 200 for this line and 206 for this line. What we can actually do is work out what's the hypotenuse h is here. We know the value of the focal length is 10 after all, and we can use this to work out what we actually need to do as a multiplication factor to make this entire hypotenuse level here be the same as here. So, how do we do it? Well, the calculation is we need to find the hypotenuse of the angle. Now this angle here is actually 14 degrees. I happen to know that because of the calculations, as I say, I've done. If we use a cosine rule, cosine of 14 is equal to 10 over the hypotenuse. So we can find our hypotenuse equals 10 divided by cos 14, and that actually equals 10.306. That means it's 103% or 103.06% of the length of the line that we've got already on our wall. That means if we take our hypotenuse of 206, multiply that by the focal length, and divide that by our internal hypotenuse, it equals the distance correcting for lens effect. I will show the difference of what it looks like with and without the lens effect in the next video. But the final thing I want to do on this video is talk about this drawing that I've just drawn at the bottom here. This is to do with the heights. Now, the way that we can measure our height, if we know the distance between the 2 points as a hypotenuse along here, and we know the z value of where the points are in relation to where the camera is, we can do exactly the same thing with the height calculation as we do with our distance calculation. And this then gives us exactly how tall to actually draw our top and bottom of our wall. And that's again what we use as part of the calculation. So when this is the actual hypotenuse, obviously these heights change. 206 means that these heights grow lower for a given angle. But when I do my corrected focal length for this length here, then I get the same lengths no matter whereabouts in the camera they actually appear. As again, you will see these in the actual next video.